This is AP Calculus. This is Unit 6 of Sparks. This is day 52. And we're going to use the fundamental theorem of calculus for particle motion in average value. So 3 things we need to keep in mind is the fundamental theorem of calculus, which says that the integral of a function is equal to the antiderivative of the function evaluated at the 2 endpoints, the limits of integration, for the antiderivative of v of t. So when we're talking about velocity, the antiderivative is the position vector. So now we have the opportunity to put the antiderivative, or the integral, with limits of integration into context. Number 2 and number 3 are talking about distance, the net distance being the difference between where it starts and where it ends, and if the particle never changes direction, so that the velocity is always greater than 0, or we could talk about the velocity always being less than 0, excuse me, we're going to get a negative total distance. But then also we have the total distance, where if the particle changes direction, then we want to know how far it traveled in one direction and add it to the how far it traveled in the other direction. And we do that by doing the absolute value of velocity. And it doesn't really matter. We can always calculate the total distance using this, whether or not v of t is greater than 0 or less than 0. To be safe, you can always do this when asked to find the total distance when you're given the velocity. And if you have a calculator, that saves you from having to find the zeros of the velocity where it changes direction. Let's try an example. The velocity of a particle that is moving along the x-axis is given by the function v of t equals 3t squared plus 6. When it says it's a non-calculator active question, that means all the numbers are going to be pretty nice. So, if the position of the particle, p, and we know at t equals 4 is equal to 72, we're asked, what is the position when t equals 2? P of 2 equals question mark. We can use the fundamental theorem of calculus by saying that we know that the velocity between 2 and 4, integral of, is equal to p of 4 minus p of 2, and that is the fundamental theorem of calculus. So we plug in what we know. So v of t, try that again, v of t between 2 and 4, v of t is 3t squared plus 6 dt. And p of 4, we know, p of 4 is 72, so 72 minus p of 2. And we're going to use this to solve for p of 2. So we find the antiderivative of this, which is 3t cubed divided by 3 plus 6t over 1. And since we have limits of integration, we don't need a plus c, so we get t cubed plus 6t is equal to 72 minus p of 2. And I forgot to mention this, but we need to evaluate this at 2 and 4. And I'm running out of room. So we have 4 cubed plus 6 times 4 minus 2 cubed plus 6 times 2, which is equal to 72 minus p of 2. So we simplify the left-hand side. Which is 88 minus 20. Solving for p of 2. We end up with negative 4 equals the opposite of p of 2. So P of 2 equals 4. So that is the fundamental theorem of calculus and how we can use it, knowing given certain information. Now we're going to find some total distance from 0 to 7. So from 0 to 7, v of t dt. So one of the things we can do is take the absolute value of that. Or we can also find if there is a place where the antiderivative is equal to 0, or actually even the velocity, because if the velocity changes direction, that will also make a difference. So let's check it out. V of t, which was equal to 3t squared, plus 6, when is this equal to 0? Let's see, divide by 3, we get t squared equals negative 2, which means t is equal to, well, there are no real numbers that make this happen. Which means this will never change direction, so we don't have to worry about the absolute value. So we take the antiderivative, which we've already done. This is equal to t cubed plus 6. T evaluated at 0 and 7. So we get 7 cubed plus 6 times 7 minus 0. And anybody who knows their cubes will know that 7 times 7 times 7 is 343 plus 42 minus 0, which is equal to 385. And since this never changes direction, and we know that because the velocity is never less than 0 or even equal to 0, this is the total distance. On the next page, we have a calculator active question. But we're going to do this problem the exact same way, but we're going to use our calculator to find some of the values. So we're going to use the fundamental theorem of calculus that says we're going to take the velocity function from 1.5 to 3.5. We're going to take the antiderivative of that. The antiderivative of velocity is position, so we take the position at 3.5 and we subtract the position at 1.5. And, well, I haven't shown you how to use your calculator to do this, which is kind of hard to do given my technological advances here. I'm going to have to try and get that up. Anyway, you can do this in your calculator where you put in the velocity function into an integral and evaluate it. And since we know the answer to that, then we plug in what we know. We don't know p of 3.5, but we do know p of 1.5, which is 2.551. And then we solve for p of 3.5. So we add 2.551 to both sides, and we get p of 3.5 is equal to 18.470. So we're missing this piece right here, figuring it out in the calculator, so I'm going to have to make sure we get that this week. But the rest of it follows the same exact pattern as without a calculator. We just aren't able to calculate this number when we have some messy problems to work with. And since this is also calculator active, we're going to go from 1 to 5. We're going to take the absolute value of v of t dt. So we would put this in our calculator, 1 to 5, absolute value of 0.5 e to the t times t minus 2 cubed dt, and this we put in our calculator and get out the answer, which is somewhere around, 913.067. I'm going to have to show you that. Next example. So we're given the graph of the velocity, and that is important, knowing that this is v of t. That at any point along here we have the slope of the position, how fast the position is changing. That's what we have the graph of. So some of the things we know is that p of 8 is equal to 12. That'll be useful. And anytime we have the integral of v of t dt, this is equal to the area under curve from a to b, anywhere along there. You don't want to forget that that's what the integral of a function means also. So, given that we want to find the position of the particle at t equals 3, well, we want p of 3, and we're given p of 8. So if we were to find the antiderivative of the velocity, come back here, from 3 to 8 of et dt, got too many of them in there, then this is going to be equal to p of 8 minus p of 3, because we're talking about the fundamental theorem of calculus. So the integral part, that is the area under the curve from 3 to 8. So we have this positive area, and then we have this negative area, and that is equal to the integral from 3 to 8 of the velocity. So from 3 to 6, we have a trapezoid with positive area, and its height is at 5. So we have 1/2 times 5, and then we add our bases, which are 3 plus 1. And that will be the area of that, and then we're going to subtract the area of this triangle, which is 1/2 the base, which is 2, times the height, which is also 2. So we have 1/2, 5 times 4, which is 20. We're going to subtract out 1/2 of 4, which is 10, minus 2, which is 8, and that is equal to p of 8, which is 12, minus p of 3, which is what we're looking for. Subtract 12, we get negative 4, so we end up with p of 3 is equal to 4. And since the velocity is measured in feet per second, the position then is going to be measured in feet. The second part asks us for the acceleration. So recall that a of t is equal to v prime of t, which is equal to the position double prime of t. So if we want the acceleration at a certain point, such as 5, so a of 5, we're going to want to know the derivative of the velocity at 5, which is equal to the slope of v of t at t equals 5. Since we have the graph of v of t, so we go up here and we find the slope right here. So we want the difference in our y's over the difference in our x's. So I have 4 minus 6, this is negative, so 4 minus 6, that is my run, so my rise is going all the way to 0, 5. So rise is 5, we're going down, 4 minus 6. We end up with our slope as negative 5/2, which means the acceleration at 5 is equal to negative 5/2, and we're talking about feet per second squared. Acceleration is in time squared. Part C says they want the net distance from 0 to 10. So we're talking about the velocity. We have all this positive velocity, and then at 6 we have negative velocity, which means the particle changes direction. So we're going to want the absolute value of the velocity from 0 to 10. But since we know it turns negative at 6, this is equal to 0 to 6 v of t dt. Now we don't want to add that part in here because this is negative. We're going to want to subtract that. That is from 6 to 10. So we're going to find the area under the curve where it's positive, and then we're going to find the area under the curve where it's negative. And we're going to make sure that those are all positive. So the positive part is a trapezoid, so we have 1/2, the base is 6, plus the top base is 2 times the height, which is 5, and from that we're going to subtract the area of the triangle, which is 1/2. The base is 1, 2, 3, 4, and the height is 2. Or we could call that -2. So we have 1/2 of 8, 4 times 5, minus 1/2 of 4. We're going to add that. 1/2 of 4 is 2. Times 20 plus 4 is 24 feet, and we're traveling in feet. You know what I just did there? I found the total distance. I got these flip-flopped. I found the total distance. What we were supposed to be finding at C was the net distance, which is the difference between 10 and 0. So for the net distance, all of this needs to move down here. We're going to find the velocity antiderivative. We already found the first one was 20, but we don't have the absolute value, so we're going to subtract out that 4 and get 16 feet. Which is what happens when you don't read carefully. Net distance was 16, and total is 24. The next page, next page, this one is left on your own. This time they don't give you a graph, they don't give you the equation, but they do give you a table. So you're going to use that to answer these questions, and I will see you next time.